Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and this week I'm joined by Sergey.
Hiya, I'm Sergey.
And for the second time ever, we are in actually the same room as each other. I've had a lot of guests on the live stream, normally remotely, but this time in person. So if you see me looking that way, or Sergey looking that way, that edge of my square is identified with. Sergey, can you demonstrate?
This edge. Oh,
yeah. Oh, yeah. You're backwards.
Yes.
Wait, you're over there. You're over there.
Yeah.
So if you see us looking sideways, we're going to try and look that way, like we do when we're on Zoom. But there we go. We're also joined by you watching at home, wherever you are. If you're joining live, you can join in with live chat, which is underneath Sergey. So underneath me is Sergey, and underneath Sergey is chat. Yes, there we go, down there somewhere. Come and say hi over in slido.com/OOMC. I'm pretty sure we're live. I think we've got a connection to YouTube. It says we're live over there. Look, I think it's good. I might do the poll in a second. We usually do this poll for how was your day on a scale from 1 to 5. I think I'll do that as well. Right. Yeah. Let's start that as well. Good. Right, time to find out if I'm actually live. People are voting, which is good. There's a sign, not 100% certainty, but some sign that we have people at home as well.
I'm sure someone would have spoken up by now if
they might have.
Anything.
Sometimes they start voting in chat and then let us know, this is weird, there's a poll running and no live stream going. Yeah, good. There was a bit that said no data that now says something other than no data. That was scaring me. Great. How's your day going, Sergey?
I'm great. I'd say pretty good 5.
Good 5. Yeah, that's what we like to see. Chat so far agrees with you that it's a 5-star day. I think I'm having a 4-star day. I've been doing a lot of cleaning data for a big database, which is
nice.
not the best. Speaking of data, what maybe or maybe not. What do you study at the moment?
So I'm doing a master's in math and computer science, or officially math and foundations of computer science, which if you know the difference, I don't. But yeah, so I am doing that, and my research project for my master's thesis is going to be verification, which I'll be talking about today.
Cool. Yeah. So we've got maths and computer science, sort of master's student on the stream to tell us about that sort of thing. Right, okay. Good to see that people are having a good day. I'm always looking out for people who are having a terrible day, who have checked in anyway, but we haven't got any of them today. We've got a few 3 stars, but I still think 3 stars is pretty good overall. Right, I want to do an ad at the start as well. So we have Promise Europe, which is a summer school being run by Promise, Wadham College, the Maths Institute, and the Clay Mathematical Institute. You might have heard of some of those things. Maybe the Maths Institute because they also bring you this. Maybe you've heard of Wadham College as one of the colleges. Maybe you've heard of the Clay Maths Institute because they'll give you $1 million if you prove one of their maths prizes from the millennium. And even if they don't give you $1 million, they might give you a summer school, which is this. You can sign up. There's a problem set that they make people do as part of the application process, and the problems are really hard. So it's that kind of summer school. Right, cool. Okay, so that's Promise, that's chat. I'm a bit worried that chat's not working. Either chat's not working, or no one wants to say anything, or I've set it so that only I can post in chat. We will work out what's going on with chat, but I think I need to hand over to Sergey to tell us about foundations of computer science and validation. Verification. Verification, always.
That's the one.
Okay, so I click there, and it goes over to where Sergey's looking.
Cool. So I have a bunch of pictures here to kind of describe what I'm doing. The key thing that I'm working on is verification, which means how do we prove that computer programs do what they're supposed to do. That's the kind of 1-sentence description, flashy. And so why do we need to do this? Well, there's a lot of systems that are kind of safety critical or things that you really, really, really don't want going wrong. For example, down here in the bottom right corner, we have this beautiful Airbus A380 airplane landing. And there was a bug in one of these many years ago where if one of the landing gear touched the ground before the others, but within a time frame of 0.2 milliseconds or something, then the computer would bug out and the throttles would stop working, and that led to one airplane crashing upon landing.
Sorry, one of the wheels touching down before the others, like is happening in that picture.
Yes, but only if they touch the ground within 0.2 milliseconds of each other.
Okay,
Or
so
something like
if within 0.2 milliseconds, the wheels touch the ground, and then the computer bugs out, and the throttle stops working.
Yes, so it's a very, very rare, very specific case when the computer would just bug out because no one obviously got that exact situation during testing while they were doing test flights or while they were programming the computer. And yeah, that led to one of these planes crashing.
Okay.
And basically, no matter how much you would have tested this, you most likely wouldn't have been able to find this bug because it's so inconceivably rare and strange that would ever happen. Similarly, here we have a little microchip, which was, I think, Pentium's A something chip, and they had a bug in it where in very, very rare occasions, maybe like once every billion or trillion calculations, it would fail to do a multiplication correctly. So it would just give the wrong answer to a multiplication problem. And obviously you wouldn't really notice this when developing it or when testing it or when writing normal programs, but this bug is really bad because if you put this in something more critical, like, I don't know, a safety critical system, a space shuttle or something like that, and one of the multiplications goes wrong, then everything can kind of collapse and break.
I guess
so.
If we think about maths computer science as well, it's a problem if you're, I don't know, checking if something's a prime number.
Yes.
And it fails in some case, which means that you thought you were doing a careful computer search, but actually your computer search was wrong and the results you're getting out are nonsense. I think it's the thing people worry about in terms of sort of computer assisted proof.
Exactly.
Okay, whether or not the computer, how do you know the computer didn't have any sort of mistakes in it that meant it?
Yeah, and usually as a programmer you'd kind of assume that your chip does all your calculations correctly, like you wouldn't even think to, I don't know, verify that all of your multiplications are correct, because that would just take an insane amount of time, and for what reason.
Yeah, not all of them, I suppose. 1 in a million though.
No, 1 in some trillions.
1 in a trillion. Okay, so it's better at calculation than me.
Yeah.
1 in a trillion wrong.
But yeah, because of that, they had to pull all of the chips and recall them, and it cost them a whole load of money. So it wasn't a very nice bug to have.
Yuck.
And so similar things happen with other systems like self-driving cars or systems that need to be protected from hackers. There's often bugs that are kind of rare or hard to detect, and you probably wouldn't be able to detect them just by trying out a whole bunch of test cases. But you still need to make them 100% secure. And so this is where the field of verification comes in. We use verification to write mathematical proofs that a system or a computer does what it's supposed to do. So giving this kind of 100% solid guarantee that nothing's ever going to go wrong, which sounds almost too good to be true. And it kind of is. I'll get into that later, but it still works exceedingly well for a lot of specific cases.
Yeah, problem: our computers are getting maths wrong. Solution: we should use maths on the computers. Right?
Yeah, we should use better maths. Exactly.
Prove that the computer works. Brilliant. Okay.
But yeah, so we need some way of reasoning about computers formally using maths, and to do this, we use Automata, which is the title of this live stream. So I'll show a little demonstration here with this very simple computer program. If you're not familiar with coding or programming in general, I'll just quickly go through how this works. So we have a while true loop, which essentially means repeat forever. If the while true confuses you, just think forever. There we go. Okay. And so we are looping these two lines. This is line 0 and this is line 1. And what it's doing is it's saying, take some value of x, whatever it is currently. We don't know what it is in the beginning. Let's just say it's in between 0 and 3. That's enough for our purposes. And then what we're saying is take the remainder of x when you divide it by 2. So for example, if it's 0, then the remainder when you divide by 2 is 0. If it's 1, then the remainder is 1. If it's 2, then the remainder is 0 again, and if it's 3, the remainder is 1 again.
I think I've seen this before. I don't know if people in chat have seen this before. It's that percent symbol, right?
Yes, that's specific to coding.
A computer
Yeah.
science way of saying the remainder when you divide by.
Yeah, so x% 2, you can think of it as, in math notation, this would be x mod 2, I think.
Yeah.
So you'd usually write
sure, maybe. Yeah. I mean, you might. Yeah, you could write something like that. Or if people don't know about mod either, then I guess it's the long form way of writing that is something like the remainder when you divide x by 2, which is a concept that people have come across, right? It's like 0 if it's an even number, 1 if it's an odd number.
Exactly.
Okay.
Yeah, that's a simple way of thinking about it.
So in CS, it's definitely basically the remainder function. Sorry to hammer on this one point, but I think we'll get questions if not. Except maybe not, because chat seems to be broken still. So maybe we'll get no questions for the whole stream. That would be quite relaxing.
I hope it fixes itself.
Yeah, okay, so percent means remainder when you divide by in notation. Okay, so your first line there, your 0th line, sorry.
Yes, we start counting at 0 because it's more computer sciencey. So we take, in the 0th line, we take the remainder divided by 2, and in the first line, or the 1th line, we add 3 and then take the remainder divided by 4.
Right, okay, so 2 things.
Yeah, so very kind of, this doesn't compute much, it just goes forever in a little loop and does these calculations, but you can imagine that, yes, that's way better. You can imagine that this could be a more complicated program that we're trying to model.
An anonymous person has saved the day by posting something in chat. It's not broken, it's just
wonderful.
Nobody needed to say anything. Thank you, anonymous person.
Cool. But yeah, so the way we actually convert this to maths, or to a more mathsy context where we can use maths to talk about this program, is by using a LTS, which is a labeled transition system. So essentially what you need to know is there's a bunch of states, which are circles like this, or ovals if I draw them on my tablet, and then arrows that go between the states like this.
Okay, so labeled transition state
system.
Okay, so you've got some circles which are the states that the machine might be in.
Yeah.
And transitions are the arrows that go between them.
Exactly.
Okay.
And let's see how we'd actually formalize this piece of code as a LTS, as a little state machine. We're just going to take every single state the program could be in. So what are the possible states? It's firstly where we are in the code. So are we on line 0 or line 1?
Okay.
And in this case, I'm going to say we're on line 0 if we haven't ran it yet. So if we're before line 0.
Right. Just at the start of line 0.
Just about to run line 0. And then the second thing is, what is this value of x? So we're saying it can be from 0 to 3. So we'll have four different possibilities: 0, 1, 2, and 3. So
maybe 0 and 3 might be the same, or
0 and 4 would be the same.
Ah, right. Sorry, you're in.
If you're
okay, 0, 1, 2, 3. Yep, no, got it. Yep.
Cool. And so literally what I'm going to do is I'm going to write out all of the different possibilities in a little grid. So we have, we're on line 0 and the value of x is 0. We're on line 0 and the value of x is 1. We're on line 0 and the value of x is 2. Or we're on line 0 and the value of x is 3. And same for line 1. So we're on line 1 and the value of x is 1. On line 1 the value of x is 2. And we're on line 1 the value of x is 3.
Nice.
There we go, pretty straightforward.
So these are the different states, and I suppose, okay, so you've got combinations here that the state includes information about both where your computer program is. I'm imagining, I don't know, because I put a robot in the thumbnail, I'm imagining like a robot character reading through the code.
Yeah,
it's got that while true loop, which is very mean to our robot character. They're going to keep going backwards and forwards, but they've got a state, I suppose they're keeping track of x and the number in memory or something.
Exactly.
But they're also keeping track of like where they are in their working. Okay.
And you can imagine if we had more variables or more lines of code, this would get big very, very fast. So if we had like, say 3 different variables, then we'd have 3 more, or we'd have 3 things after the L0 or L1 and a proportional number of states. So doing this kind of just brute force approach of let's list out every single possible thing isn't really practical in real life, but there's better methods of modeling programs than just this one that I'm showing here.
Yeah, chat says we're only using integers, and I think we're only using small integers. Yes. We're imagining that gosh, just to save the poor little robot character's memory, we're imagining the only possible starting points are 0, 1, 2, or 3, and then we're going to see what happens next.
Yeah,
you can have but you can have more complicated machines that need to be able to cope with more complicated integers.
Exactly. Yeah. So you might have some system that uses floating points, so decimal numbers, but we're not going to go into those now. I think this is complicated enough.
Yeah. Okay. We'll stick integers only.
Yeah.
Good.
But okay, so now we've got the states. Now we need to draw the transitions. So how are we going to do that? Well, let's just see what happens. For example, starting at this state over here. So if we're before line 0, so we're about to execute line 0, and then our value of x is 0. After we execute the line, x stays at 0 because 0 is an even number. So when you take it mod 2, it stays even. Or sorry, the remainder is 0. So the value of x stays at 0, and then we move on to line 1. So our transition goes from here to here.
Sure. Okay. So moving down because we're going from line 0 to line 1,
yes.
And the value, sorry, so our value, the thing in the computer's memory, the number of x was 0, 0 mod 2, or the remainder when you divide 0 by 2 is still 0.
Yep, exactly.
Cool. Okay. More arrows. This feels like the sort of thing where people can join in at home.
Yes.
If they can.
So quick little challenge. Can you draw in the arrows faster than I can?
They are pretty quick.
Perfect. But yeah, in this case also what's nice is that we only have one option where to go from each possible state. So we don't have any ifs, we don't have any whiles, we don't have any kind of branching or weird stuff going on. We literally have a program that says this happens, and this happens, and this happens, and this happens.
But this method could capture things with branching.
Yes,
right?
yes.
Because you're sort of asking for every line of code and for every sort of set of numbers in the computer's memory.
Yeah.
What happens next?
Exactly.
I guess it's deterministic. There's no randomness in this. So
yeah, but like there are cases, and we'll see them later on, where from one state you'd have two transitions. So this could model, for example, an if statement happening. If something's true, it goes to this state, but if something else is true, it goes to another state.
Maybe if it's sort of random, or depends on some sort of hidden variable that's not something in our state space.
Yes,
so
exactly.
We can't determine which of them. Okay, so different ways to model these. I like that the line that we're on is part of the state space. So we're keeping track of like where the pointer is. Okay. We're keeping track of where the robot character is looking. What's a pointer? It's something I feel embarrassed to ask.
Pointer is location in memory, but
no, I can't. I've said the wrong word.
Instruction register, maybe, if you want to get technical. But anyway, but yeah. So what we'll do is we can literally just draw the lines in. So I'll go through this quickly, not to dawdle on this point for too long.
You draw the arrows, and you've got one that you made at home, and I'll read out some things from chat.
Yes.
So Hamish in chat thinks that the following is impossible. Line 1, x equals 2. But it's impossible to get to line 1 x equals 2. I guess if we draw all the arrows in, we can think about that. That's the question. Once you've labelled all the possible arrows in, is there anything pointing at line 1 x equals 2?
Yeah, exactly. That's actually a really good point, because we'll get back to this later. Once we've drawn in all of the arrows from all the different states to all the other states, we can actually start reasoning about whether, for example, some states are reachable. Like, we'll see this example later on. So if we start with x equals 0, and then we make our way through this graph, and I realized I just forgot to put in one of the arrows. There it goes. Yeah, so as you said, Hamish, that's totally correct. So if you go around this graph just like this, following the arrows, you'll never be able to reach this number 2.
Yeah, no matter where you start, right? There's no arrows pointing in towards it, because I suppose the remainder is never larger than 1.
Yes.
But also, you don't have to think like that. Once you've got all the arrows, you don't have to remember what the logic was or what the maths.
I suppose, yeah, this kind of abstracts the code away. So we've got this completely arbitrary state system. But the only way you could get to this state over here is by starting in.
Oh right, okay, yes.
Or by starting in this. I just deleted stuff. By starting in that state over there.
I guess we've abstracted away the concept that the robot will probably start at the start of the code.
Exactly.
If it started at line 1, then anything's possible.
Yeah.
Okay, we've abstracted that away because...
Exactly. And also we don't know what the initial value of x is. So x could be 2 initially. We just, we haven't defined that anyway.
It could be, yes.
Yeah. We've never said that x is 0 in the beginning.
Okay, yeah, okay. So there's kind of lots of possible starting points if you allow the robot to start executing code from the middle, which...
Exactly.
I'm not going to say no programming language does that, but that's...
It is a bit of an odd case, yeah, but you do come across it sometimes.
Yeah, well, how does Mondrian work? Anyway, never mind.
Okay, so I've just filled in all these arrows now, and it's time to start actually reasoning about these transition systems. So how do we actually determine whether something is true or false in a given system? Mm-hmm. And for that, we have this thing called a linear temporal logic, or LTL. And so I don't know if many of you have seen logic before. If you have, then you've probably seen these these over here.
So you've got symbols for and or over there.
Yeah.
Not, and then that's like an if, like an implication.
If then, yeah, exactly.
Okay.
So you've probably seen these first 4 symbols. They're just standard logic symbols. And some people might draw the and like this and the or like this. If you're doing probability, for example.
Yeah, okay. Or set theory, where you're doing the intersection or the union of some sets. Yeah. Okay.
But here we just use these kind of logical symbols for and or. If they confuse you, you can just write out the words and or. It's
yeah, we'll try and keep this on screen because we've got some new symbols as well that probably nobody has seen. Although do let us know in chat. If you've got 4 more, what do they say there?
Yeah, so these are I actually only recently found out about them when I took a course on this topic exactly. But yeah, these 4 are temporal operators. So temporal means talking about time. So all of these talk about what's going to happen in the future in some way. While these first 4 are just logical operators which say that 2 things happen, or 2 things are happening at the same time, or something's not happening.
Okay.
And so these 4 temporal operators are next, always, eventually, and until. And I can give some examples of that. So next means that if we're somewhere in our transition system, if we're somewhere in our little graph that we drew earlier, then in the next state, something will be true. So once we move 1 arrow forward.
Okay.
And the square means always. So that just means that no matter how many steps we do, something is always true.
Right. So if it were the case that, this is not true for your previous code, but if it were the case that x was like always 0, I don't know, if all the arrows pointed at states on the very left of your chart somehow, it's not what the arrows look like at all, but if they always pointed at things on the left, then following the arrows you would always have x0.
Yeah, exactly.
Okay. You could say.
Yeah, so you could say, for example, informally, always x equals 0.
Yeah, cool. Okay.
Or always x not equals 0, for example.
I think I'm imagining some pretty stupid code that just line 0, x equals 0. Line 1, x equals 0. Sort of make sure that it keeps setting x to 0. It's like bouncing between the lines, so I'm changing states, but if you follow the arrows, it's always x equals 0. Right, good.
But you can use these operators to define some kind of interesting properties that you might find in the real world. For example, if you have a road with 2 traffic lights, and you have green 1 means traffic light 1 is green, and green 2 means traffic light 2 is green, and they're on intersecting paths, obviously. Then we could, for example, say that the property that they're never green at the same time would be always not green 1 and green 2. Does that make sense?
Wait, yeah, I'm going to have to unpack it, sorry.
So green 1 and green 2 is saying that they are on at the same time. So
yeah, okay, that's fine. That's the intersection, that both lights are green at the same time.
Exactly, yeah. And then this here is saying, oh, I don't want that to happen. So I don't want both lights to be green at the same time, otherwise cars are going to crash into each other. And this square here is saying that I want that to always happen. So no matter what state I'm in, no matter what time it is, I never want the 2 lights to be green at the same time.
Cool. Okay. Yeah. So that always not just right now, but all the way through the future.
Exactly. Yeah. Another fun one is when talking about computer programs, we might want to know whether something terminates or doesn't. So whether a computer stops calculating or whether it will run on forever. And we can have a phrase terminates, which just encodes whether a program stops or not. And then we can write a LTL formula, eventually terminates.
Right.
There we go. And that just says at some point in the future, the program will stop running.
Which might be good news if it's finishing a calculation.
Exactly.
It might be bad news if it's keeping the plane in the air. But yeah, okay. Maybe it's an important thing to know whether the thing terminates or not.
Sure.
And terminating in finite. So terminating in finite time means sort of eventually.
Exactly.
Okay.
Yeah, eventually. Yeah. But if you've studied any, or if you've seen any popular computer science, you might know that this is actually an undecidable problem. So you can never come up with an algorithm or a computer program to decide whether that's true or not for any given program.
Right, that's got a name, hasn't it? That's
yes, Turing's halting problem.
Right. Okay. The problem of deciding whether or not a computer program halts.
Yeah.
You can't have a computer program.
Exactly. You can't have a computer program that always answers that question correctly and also itself terminates no matter what program you give it.
Right. Okay. So some of these questions are going to be very hard in some sense.
Which is funny because you only have one symbol and one statement here. It doesn't seem like anything too complicated, but actually,
right.
This is something you can essentially never decide. This doesn't mean that you can't write programs that'll check this for specific cases, right? You will be able to write programs that check whether one specific program terminates.
Like that one we saw before, I know it's not going to terminate.
Exactly.
It's going to keep running while true forever.
Exactly. And it was obvious. We could just see from the loop that it'll just keep looping forever. So in specific cases, this is possible, but you can never write a program that decides it's for any possible input. I
know a proof of that, but I don't want to sidetrack us too much, so I might put it in the further reading.
I think that's a good point.
If it's your first episode watching Maths Club, we do further reading, which is kind of blog post. Posted the day after the stream, containing all the things that we didn't have time to say, and other things too.
Cool. Yeah.
Yes. Okay. We've got some new symbols.
Perfect. What can we do with them?
Yeah.
So let's go back to my transition system example for a second. Now, if you start in some state, let's say we start here, and so this arrow coming from nowhere just means that's where we start.
Okay.
From the state, you'll be able to take a path. So the path being, we go here first, then we go here first, then we go here, then we go here, and keep looping forever.
Yeah.
And in all of these transition systems, you'll be able to find these paths. Sometimes you'll have multiple paths. Here, in this case, we only have one. But sometimes you can have even infinitely many paths in a transition system. And so we want to decide, using our newfound logic, whether for some specific path a formula is true or not.
Right, so a formula is some combination of these symbols and statements, like you're always not green 1 and green 2.
Exactly.
Okay.
So this here would be a formula, and we usually use this Greek letter phi to because we want to be posh and fancy and use Greek letters for our math. So if you see this phi, it means just formula.
All the Greek people watching are like, oh, there's nothing posh or fancy about Greek letters, right?
No, exactly.
Okay, I've just thought, so proving that your traffic lights never do this does seem quite important. It seems like you have to analyse all of the possible sort of state transitions or arrows of what your traffic lights might be doing, or the computer inside them is doing, I guess. Yeah. Cool. Shall we?
So here are some examples of this, and now this is imagine just taking one path out of your transition system. So go state by state by state, and they form this little chain.
Okay.
And here's an actual description of what these symbols or operators or logical thingies mean when you look at them as paths. So if your formula is just one letter, A, for example here, then that just means that you want it to be true in the first state.
Right, okay. So here and now, these statements refer to, by default, just right now.
Yeah, exactly.
You're in this first state. Okay.
Yeah, you're in this first state.
So you've got an example.
Starting at this first state, A is true. And then these gray question marks mean that we don't really care what happens after that. So our formula doesn't care whether you have B's or A's or C's after that. It just cares whether there's an A in the first state.
Okay.
Now this not A over here, so again this little squiggly arrow thingy is a not. It's saying that in the first state I want there to not be an A. Also pretty straightforward. So anything that doesn't have an A, for example, a B or a C or a BC would satisfy this.
Right, because the state can have, we're going to see in a second, the state can have multiple letters, it can have multiple properties at that moment. Like how the first example we showed us had at each state there was some information about the line number we were on and some information about the value of X. So you can have kind of multiple,
exactly.
In this case letters, but properties of what's going on.
Sure.
At that state.
Cool. Then our hat thingy, so the and or the conjunction if you want to be really fancy mathematical, means and, so you want both A and B to be true.
But it's still here and now in the current state.
Exactly.
Okay.
Yeah. And this one, A or B, that just says I want one or the other or both to be true. So as usual in math, we kind of don't care if both are true. They can be, they can also not be. So anything in this case, if we had a be like that would be okay, or if we just had an A, that would be okay also.
Okay. Right. Inclusive or.
Inclusive.
Okay,
exactly.
But still in the here and now, just like these are all properties, you prove them or check them, I guess, by just looking where you are right now.
Exactly.
Is it true? Are both traffic lights green? I don't know, go check them right now. Cool, good.
Yeah.
It's not very temporal yet, but you've got the temporal ones coming up.
Exactly. So we haven't talked about time yet, but now we get to the temporal operators. So we start with the next one, which is quite simple, is just to look at the next state and check whether the formula is true.
Okay.
And here you can do some sort of combinations of the stuff we had previously. So for example, if you had next A and B, like that,
okay,
then we would want that in the next state A and B are true, just like that.
Okay.
So the operators that we have here, they're not limited to just like being on their own. We can combine them in any ways you like. But next means just look at the next state, see if it's true or not.
I'm already finding I'm forgetting them, so I'm just going to scroll. Don't mind me.
Yeah, they're a little tricky.
Don't mind me.
Perfect.
Just going to put this here.
Yes, wonderful.
Ooh. I'm also going to stretch it. There we go. Perfect.
Wonderful.
Professional live stream. Yes.
We brought it together.
Together.
Now, always is pretty self-explanatory again. So whatever is inside the little box or after the little box, you want it to always be true, no matter where you are in your state, or sorry, in your transition system.
Future facing though, so we never care about the past.
Yeah, you never care about the past. So all of these statements only talk about the future.
Okay.
Because if something's happened in the past, you've already checked it with an operator before.
Okay. I guess we're assuming the plane hasn't crashed yet, and we're thinking about proving that it won't in the future. Okay, good.
So your operator always doesn't crash kind of implies that if it would have crashed before, you would have already noticed.
Tell me about eventually.
Eventually, so this just says at some point in the future, doesn't matter when, as long as it happens at some point in the future, we're okay.
At least once.
At least once, yeah.
Maybe more than once. Okay.
Exactly. So we don't care about what happens here. We want one A, and then we don't care what happens after.
Okay.
Very straightforward. Again, we'll see what happens when we combine these later on. They let you express some very spicy stuff, but on its own, nothing too fancy going on. This until operator, so the big U.
Not to be confused with OR, I guess.
Yes, they're a little bit similar.
Your OR is a sharp shape, and your until thing is new. Here it comes. Yep. Okay.
Yeah. So the until is kind of like the eventually. It's saying we still want A to hold eventually. So at some point in the future, doesn't matter where, doesn't matter when, we want it to hold. However, also before it does, we want B to hold.
Okay. So you want to see some number of B's. Doesn't matter how many, but some number of B's.
Yes, as long as there's always some B's in your states.
Okay, so it might be B's forever.
Wait, no, sorry, I misspoke. So you want A to hold at some point, like for example here, and then before that, at all times, you want B to hold.
Right, okay. So it's a combination. It's stronger than eventually A.
Exactly.
It's eventually A, and also before that, I want to see B's all the way through
Yes.
the other letters.
Exactly.
Okay.
So this is maybe the trickiest operator in that it expresses a lot of information. And actually, you can show that the box always and the diamond eventually, you can actually express them using the until operator. So the always and eventually are kind of useless or they don't bring anything extra to the logic.
I was thinking about building until, maybe this exercise for people at home, but I was thinking about building until out of the other ones because it felt like a kind of super eventually to me.
Yeah, you can do that as well. So you can go in both directions.
Okay, right.
So kind of
Homework.
you either need the eventually and always, or you need the until, and either way you'll have the full power of the logic. But yeah. Fun little exercise to do at home.
Almost the kind of language challenge, right? To say, can you use these words? The words are always, eventually, and you can make some statements about A's and B's to express the sense that you eventually have an A and the B's until you get to that point. Like B until you see an A eventually.
Exactly.
A couple of bits of admin from chat. How long will the stream be? It's going to be 1 hour. We've got 25 minutes till 6 o'clock. And if you want to contact us, there is a Maths Club email address, which is oomc@mathsdogs.ac.uk. Jonas says, can the eventually operator be formalised in some areas of math? It seems to behave like filters do in topology.
Ooh, that's a tough question. I'm not sure what a filter in topology means.
Neither do I.
If you can elaborate on that, I'll get back to you.
Yeah, but, this might be the sort of thing where we need it to be an email so that we can also go and look stuff up. But I think, hang on, so we were just talking about formalising it as if you like, it's a property of these sequences. So if you prefer to think of everything as a sequence, for a given path, there's a sequence of letters, then I think you can formulate this as a sort of property of the sequence, right?
I suppose, okay, yeah, so...
There exists an n greater than 1, or maybe just greater than 0. There exists an n greater than 0 such that the nth term of this sequence is equal to value.
Yeah, actually, that's true. So you're probably thinking of something like convergence or...
I'm a little bit, because I've done some courses on properties of a sequence of numbers. I think people watching might have seen the sense that a series of, I don't know, decimal numbers or something might be getting closer and closer to some limit. I'm just imagining, you see, eventually it's pretty close.
Yeah, exactly. And actually, there are concrete mathematical definitions to all these operators, so you can write them out in pure first-order logic. And then if you do that, then the definition of eventually will basically look like the definition of convergence from analysis or topology. Because there exists some n before which, after which, etc.
So they maybe look woolly because they are kind of like everyday words to do with time.
Yeah.
But that's actually the power of it. The kind of beauty, the ambition, if you like, is that we're trying to talk in sequences and talk about properties of sequences that line up with, as close as we can, perhaps, the everyday use of words like always and eventually. This comes from, I think, people trying to do philosophy to do with time, which I don't know, is up to people at home whether they want to. I'll put a link in the further reading for philosophy of time.
Sure. But yeah, the power of this is that you can kind of reason about these systems without knowing the exact formal definitions of what these symbols mean. So we can kind of intuitively know what always means. We intuitively know what eventually means. So when we get to the puzzles soon, you don't actually need to write out a whole bunch of math. You can just kind of reason about it in your head or on a piece of paper.
Okay. We've got a few of these, so is this 2 more? Yeah, and then a puzzle. Good, okay.
Cool. Yeah, these are just some more complicated examples of combining things together, which I'll kind of skim over. Won't go into horribly much detail just because they're contrived on purpose. But yeah, so here we have the implication R, which means the if-then operator. And it's saying if we see an A in the first state, then we'll see a B in the second state.
Okay.
Because the next B means we see a B next, or one step in the future.
In my experience, people find if-then very confusing.
Do they? Okay.
Because in your example, your example is consistent, of course.
Yeah.
The claim is if A, then B, which I'm happy, right? Because I can see an A, and also then I look at the next one and see a B. But yeah, if you put
I put
B question mark.
exactly that also
Right.
holds.
So this still satisfies the formula.
Yeah.
And I think people really don't like that. The formula says if A then B. It doesn't say anything about if B, or if not A. What's supposed to happen if it's not A right now? Well, it doesn't say.
Yeah.
So anything goes. I think that's the bit that worries people about implications. You can build that statement out of. So you can build that sort of thing out of and not.
Yes, you can.
Or and not.
Or an and not.
And not and or.
Some
you build
combination.
and?
You can do and not or not. I think both are fine.
Okay, quick chat about logic gates. Can you build and out of or and not?
Yes.
Oh, goodness
right?
me. Okay, so how many of these things do we actually need?
Yeah, not many. A lot of these are just kind of syntactic sugar, making our life easier by adding symbols, but a lot of them aren't necessary. And actually, when we do this for real in the real world, we kind of try to reduce it to the minimum possible number of symbols so that we can more easily reason about what happens.
So they're just here to be helpful for humans reasoning about them.
Exactly.
Okay, cool. You've got a complicated example, which is
this saying always
square is.
always the previous thing holds. So it's
always, if you see an A, then the next one is
exactly
B.
Because this one is saying just in the first state, if we see an A, then the next one is a B. But this is saying no matter what state we're in, if we see an A, then the next one's a B.
Okay.
So here, for example, we see an A, the next one's a B. Here we see an A, the next one's a B. Here we also see an A, so the next one's a B.
If you see someone crossing the road, apply the brakes on your self-driving car.
There we go.
Forever, not just right now. I don't mean right now, check if there's a person there. I mean always. This is me explaining to a self-driving car how to. I want to prove that for all time.
Yeah.
If A, then the next thing that happens, braking.
Exactly.
Good.
Your A is human on the road. Your B is apply brakes.
If then is not quite if and only if. In fact, that's almost. Yeah, so it's not if and only if.
Yes, we also have this thing which is if and only if. But,
right, yeah,
so
okay.
We're not going to go there right now.
Running the water. Okay,
I'm going to go to my puzzle. So
carry on.
If you're at home, grab a piece of pen and paper if you have one, and let's do this.
I've forgotten to follow you.
This may be a little tricky one. So we have two formulas here. One is eventually always A, and the other one is always eventually A. And you might think, well, they sound very similar, right? Surely they're the same. But actually, no. These two formulas mean completely different things. See if you can come up with a reason why.
I need my key again. I'm going to get the key. I'm going to get the key.
Oh, yes, of course.
But one of them is always eventually A, and one of them is eventually always A.
Yes, exactly.
And okay, so I'm going to remind myself of the definitions because that's what I do when I see a tricky puzzle. If you're playing along at home, we're looking for a sequence or two sequences of letters written in the circles. You can use as many letters as you like, but probably just A's and B's is sufficient.
A's and B's is
A's and B's written in the circles, such that for one of them it's true that always eventually A, but not eventually always A, and the other one the other way around. That's puzzle one.
Yes.
Okay. So always means from now on.
Yeah, from now on forever.
Okay. From now on forever. And eventually means after some unspecified amount of time it'll happen.
Yeah, exactly.
And if that thing is itself something always happening, then okay, so eventually always is this thing that Hamish has put in chat. Thank you, Hamish. Which is some question marks, so there's space for moving this around. Eventually always A means after a while, and I don't know how long, doesn't matter, it'll be A forever afterwards.
Exactly.
Eventually, open bracket, always A, close bracket. Okay.
I just realised this puzzle may be unsolvable actually. Well, anyway. Well, it's half solvable, that's for sure. You can do one of the directions. You might not be able to do the other.
We should probably have play tested the puzzles.
Yeah. Well,
okay.
It's a good learning experience for all of us as well.
Always eventually A means that it's always the case. Whatever's going on right now, it's always the case that it's eventually A. So
Yeah.
we'll see whatever is going on right now, we will be able to eventually see an A. Well, I'm going to say another A, because once I've seen that one, it'll still be true that there'll be eventually an A. So there's another one. So I think, which one is that? It's the thing in chat as well, I think, which is that always eventually A means something like infinitely many A's.
Exactly. Yeah. There you go.
Possibly spaced out quite a lot.
Mm.
So A on all of the prime numbers or something.
Yes.
And this one, eventually always A, means it gets stuck on A at some point. So like things that are bigger than 1,000.
Yes. There you go. Perfect.
But is the problem for your original, as your, so you've
Yeah,
got cold feet about the puzzle to find one that does one and not the other?
Let's see. Yeah, so I'll draw what my solution was going to be, and then I'll explain why it doesn't quite work. So let's see here. If we just have
the one that gets stuck on A is definitely going to have infinitely many A's.
Exactly. Yeah.
The one that does A infinitely many often might or might not have all of those A's, A forever onwards.
Yeah.
So one way round implies the other.
Mm-hmm.
Oh my goodness,
Precisely.
this is some like...
So my example was, if we have, in the top one we just have one B and then infinitely many A's afterwards, or an infinite chain of A's rather. And then in the second one we have an A, then two B's, then an A, then two B's, and that repeats forever.
Right.
So here in the first one, or let's start with the second one actually.
Mm-hmm.
So in the second one, always, eventually A, that's true, right? Check. Because no matter where we are, we're eventually, in at most 3 steps time, are going to see an A again.
Yeah.
So this statement is just saying we're going to see infinitely many A's in the future. It doesn't matter how they're spaced out, just as long as we see infinitely many of them. Yeah. While this other statement, which is eventually always A, that's not satisfied, because that's saying, well, at some point in the future, we're going to get stuck in a loop of A's and we're going to see nothing else.
Okay. Yeah.
But in the top one, both statements are satisfied, because we both have infinitely many A's and also we get stuck in the A's.
Right.
So I don't think there's a way to
do
one
the other with not the one.
Yeah. Exactly.
Yeah, Joe in chat, agrees. I think
Exactly,
that this applies to both. I'm trying to think of an English language sentence that demonstrates the difference. I think I've got it. One is, I always eventually do my homework. It's like a statement about me being quite lazy, but I always eventually do my homework. Mm-hmm. That's quite different from, I eventually always do my homework.
Yeah.
Like I get stuck. It doesn't quite work, does it? I eventually always doing homework. That's not like different, where I get stuck in the state of
doing homework forever.
The state of doing homework forever onwards.
Very relatable as an Oxford student.
Yeah, I guess I'm saying my homework looks a bit more like the second case than the first case. Yeah. Regular but not perpetual.
Yes.
Although perpetual would satisfy both. Good.
Cool. Well, this is a good puzzle. So actually someone mentioned in the chat that surely an infinite chain of A would hold for both, and yes it would. That's true. The reason I kind of showed this puzzle is because we're able to find this chain here where one of the formulas holds and the other doesn't. This is a proof that these two statements aren't identical.
Yeah.
So if you need to prove that two logical formulas are different, you just need to find an example where they're different. And for example, just saying that, but the chain of A's satisfies both of them, that's not a proof that the formulas mean the same thing. They mean different things, just like sometimes both of them will hold at the same time.
Okay. Yeah.
Cool.
Good.
Ready for our next puzzle?
I think so. We've got 10 minutes on the clock. Is that enough
good.
For a second puzzle?
Yes.
Okay. Where do we go?
Yeah, let's go over there. You can
I'm following
follow
you.
my cursor. Yeah.
Puzzle 3? Yeah.
So puzzle 2. Sorry.
Puzzle 2. I thought we were skipping 2.
We're not going out of order. Okay. So now time for a very similar but slightly different case. So now instead of having just one path, we have this state machine that we saw in the beginning. And now we want to find out whether these formulas are true or not in the full state machine, not just for one path. And the way we get around it, not being just one path, but you possibly having infinitely many paths or multiple paths, is we just say, well, a formula is true if it's true for all the possible paths through the graph. So in this case, actually, it's not too difficult because we only have two paths. Either we start here and then go here and loop here forever. Oh, there we go. So you start in this state and then you go and loop in this one forever. Or the other one is you start in this state, you go down here, and then you go here and you loop in this one forever.
So there's a choice of path in this one.
Yes, but there's only one choice, which makes it kind of nice to reason about.
I see. So this might be some sort of maybe there's some secret variable we haven't understood that determines which one happens, or maybe it's...
Sure, it could just be like an if-then else statement in a programming language.
Sure, where it's based on some variable that's not A,
yeah,
so we can't decide which one it's going to do from these letters, perhaps some sort of choice, or maybe it's random. Maybe there's a branch of maths called Markov chains, which I think is not really what we're talking about, but I'm going to crowbar it in, where these things happen with certain probabilities, and you can study the kind of probability that you get stuck in a loop, or the probability that you end in a particular state.
The research I'm doing now actually considers LTSs where you put probabilities on the transitions.
Oh, right, okay.
So here you could go here with 0.5 probability, or well, let's make it more interesting, 0.6. And you'd go here with 0.4 probability.
Yeah, so then...
And then you can kind of calculate the probability of a formula being satisfied, exactly.
Sure, okay, you want to see a B today? Well, it looked like there was a 40% chance of seeing a B. Okay, I do need my cheat sheet again. I'm going to stop following you. Would you mind? I'm going to keep this on screen. Would you mind grabbing the kind of cheat sheet for what the symbols mean? Because
of course,
I know we just demonstrated that diamond and square are different and the order matters. Thank you.
And that should be fine.
Thank you.
Cool. So do you want to work through some of them?
Yeah, so we're coming in from that first one.
Yeah, so we're always coming in from this transition.
Yeah. Somebody says, "What does circle mean?" And we've got you. And then there's some text in chat. Let me read this out. With eventually, oh no, they're still asking about eventually always A. There's a person who said, "Can you do eventually always A just by doing?" No. They asked.
With eventually always A, could you do BBA, BAAA? I guess the A's repeat forever, because you could have a lot of A's in a row, but then AB, because the always A could come later.
Yeah.
Yeah, so that does satisfy eventually always A, because at some point in the future, when your infinite chain of A's starts, the always A holds.
Yeah.
So yeah, that would satisfy the formula.
If I'm eventually always doing my homework, that perpetual stuck state of always doing my homework, it doesn't rule out that I might do a little bit of homework first and then before getting stuck. Yeah. Eventually is quite permissive as a kind of word, like.
At some point in the future, just pick a time, and that's your time when you have to start doing your homework forever.
Maybe it's not in English language. If I say, eventually I'm going to, I don't know. Eventually I'm going to get stuck in this state. I'm going to dip my toes in a bit first, but eventually I'll get stuck. You can make that distinction, I think, in everyday language. Maybe not my getting stuck on your homework, but yeah.
Sure. Just to make this problem a little more straightforward, this puzzle is really nice because there's only two possible paths, which are precisely A forever.
Yes, if you use that first arrow at the top.
Exactly. And then A, B, C, I'll just draw them like this. Yeah. And then A forever.
Yeah.
So all you need to do to check these formulas is you need to check whether they're true for both of those paths.
Okay, and so statement 2 over here, formula 2, sorry. This one just says, it says the next state is A.
Yeah.
I'm imagining that I am here.
Yeah.
Right.
So you want to check that no matter which of these paths that you're in, so either we're here, the next state is A. So in this case it is, but in this case it isn't.
I might go down here instead.
Exactly. So that means that the formula isn't correct.
Yeah.
Or the formula is false.
Not keen on statement 2. I guess I almost got tricked because the formula A on its own, like right now, A.
Yeah, that would be true.
True, because when you start, you definitely see that A at the top left. Okay, I've got that right. Next is where we're going next. So it
So-
could be one of the others.
I'll cross out
Okay.
that one as
Not that
as
one.
false. Yeah.
And in chat, they're not keen on always A. So statement 1, they're not keen on that because you could go via the
Exactly.
B.
Perfect.
Joe thinks, and Eunice. People in chat think, 3 people in chat think that all of the others are true, though.
We'll see here. So, always eventually A. What does that mean?
Well, we discussed this just now,
We
right?
did,
That if you get stuck in an infinite chain of A's, well, infinite always A, if you get stuck in that, then it's both true that always eventually A, and also eventually always A.
Exactly.
So I think that's 3 and 4.
Yeah. So in this case, this is an example of where both these hold at the same time.
Right. Okay. Because we've got that infinite chain going on.
What does phi5 say?
Next, always A. So I think that's true, just like reading left to right.
Exactly.
If I go next step and I go next step, then it's always A.
Precisely. Yeah. So we start at this one, then we go 2 steps in the future,
Right.
and we want always A to hold from then on, and clearly it does because we just get stuck in the infinite loop of A's.
Okay. So this next thing is more of a kind of modifier, or no? What's going on? I'm with chat. I want the formulism after this.
The next operator is actually really annoying to reason about in actual real world applications, just because it makes everything into a mess. Because you can have chains of nexts and they become really confusing. So oftentimes you'll research what happens if you just forget about the next and you only have all the other operators. But it's called verification without next, or verification of LTL minus next.
Without next.
Yeah.
But you're still using some of the temporal always and eventually.
Yeah,
and
so using all the
until,
others.
right, okay, the ones that have a bit more flexibility, rather than being specifically the next number. And then this last statement says, the next one's C, or it's always A. And that's true, because of the 2 different branches.
That is true. Yeah. So this is just
Like
encoding the 2 different possibilities. You're either getting a C in the lower branch, or you're always getting A's in the top branch. So this is true as well.
Can you remind me what was it LTL?
LTL, yes, linear temporal logic is the fancy
Linear
name
temporal logic. Is that linear temporal?
linear
like,
temporal, yes.
like linear time.
Yeah, because there's also CTL, which is
Don't say complex time.
no. It's
say
branching time logic. I don't know why there's a C there. It does stand for something reasonable, but so these properties we're discussing here, they work in some notion of linear time. There's also properties that work in branching time. So you consider situations where you can start at states later on and then branch from those. Anyway, so.
Okay. We are running out of linear time, I'm afraid.
Yeah.
So do we show them one last puzzle, or do you want to?
I think I can show one last puzzle,
screen.
And then give that as homework if anyone's interested.
I should follow you.
Yeah. So this puzzle is the exact same as before, except our state machine's a little more complicated. You'll notice that we have 2 possible inputs from here and here.
Oh, we might start in various.
Exactly.
We got a choice. We might start there or there.
Yeah.
Okay.
And now you can also see that there's infinite possibilities for the paths you take. So there's not just 2 paths, but
there's like some looping stuff going on.
Yeah. So you can choose to take this loop a whole bunch of times, and you can choose to take this loop a whole bunch of times. And anyway, it's a bit of a mess, but you can still try to see whether these formulas are true or not.
I suppose my question is, so we really let people try and decide whether these formulas are true or not. I guess my question is, are there algorithms for some of these? We said earlier on that there's no algorithm that does every question of this format because of the halting problem. Can you get a computer to do this instead of getting chat to do this?
Yes, so the entire field of research of formal verification is actually how do we get computers to automatically decide these LTL formulas. Right. And so the way that works is you first convert them to some sort of first order logic formula or a whole other state machine. And then you can put these LTSs, so these program state machines and the logical state machines together and do fun stuff that combines them and sees whether the formula is true or not. But yeah, so
that's the punchline. You're teaching computers to apply the logic to check that your computer programs can correctly do computations, including maths.
Yes, exactly.
So
we use maths to reason about computers, to reason about maths to reason about computers.
We may be stuck in some sort of loop.
We could be, yeah.
The computers can decide. Cool. Okay. we're hitting 6 o'clock. Anything else you want to tell them to wrap up about?
Not really. Yeah.
Okay.
Computer science is fun. Highly recommend it.
Yeah.
If you want to study these sorts of things related to logics and automata and games and all these fun stuff, then check out the research that the Automated Logical Reasoning group at Oxford does. We have a lot of cool stuff.
Oh, nice. Yeah, I think it's been really good insight into, for me, what the foundations of computer science might look like and what the kind of role of mathematics in verifying computer code could be like to convert things. I really like that first step actually of converting the computer code. There was briefly some code on screen, blink and you miss it. Converting that code into a kind of mathematical structure of like, well, it's just a sort of state transition, right? That's maybe finitely many things it can do. Like sort of converting it into a maths problem, because that's the sort of thing we do a lot. Somebody in chat anonymously says, thank you. Which I think you can
Thank you too.
Thanks for watching. Good. Right. Okay. As discussed, we're doing 1 hour and it's 6 o'clock. And there's an email address on screen. There's also a website where you can find other episodes of the Oxford Online Maths Club. We do this every Thursday at 5 o'clock. You can watch us live. That's 5 o'clock UK time. Or you can stream this and over 90 previous episodes on the Maths Club page. Free of charge whenever you like. You can even watch them at double speed, I'm told, if you want to get through.
Very handy. If you found these puzzles easy, you can rewatch them at double speed.
Rewatch them in non-linear time.
Yes.
Accelerate through. But I think we'll leave it there for Automata. So thank you very much, Sergey, for coming on Maths Club. Thank you for people joining in chat. Have a nice evening, everyone. Have a good weekend, and we will see you in 167 hours for another episode of the Oxford Online Maths Club. Take care. Good night.